Welcome to another ShedMate workshop. It's Artur Bessoni here, professional engineer and managing director of ShedMate. And I was looking forward to this workshop. We're going to talk today about engineering Demystified for Shed business owners. We're going to discover why engineers and shed business owners sometimes they hate each other and what's going on, why there's so much frustration with communication with engineers, they never get back and all of that. Why is that? So I want to explain some concepts to you in the face of that communication between these two parties. So if you run a shared business, you probably faced this before. So why do engineers make everything so complicated? Why do their reports always look different? I just sent a report to them and it came different. Now I have these massive footings. What's going on? And why does it feel like they're slowing me down instead of helping me move faster? I've been talking to many shared businesses around Australia, and there is something that repeats all the time: delays in terms of engineering, inconsistent assumptions, extra costs, liability fears. What's going on there? So, if you haven't been to other workshops, allow me to introduce myself very quickly. I am both a professional engineer and I own the shed business myself that was supplying cold formed steel. So I lived on both sides of this table, right? Having these discussions with other engineers who were signing on the projects that my business were in, and I've also been involved in structural design, in which we're developing structural design for other firms. So my goal in this webinar is to translate to you this engineering word in simple terms that makes sense for your shared business. And we're going to cover exactly why those assumptions matter, what are these assumptions, what engineers are really doing, and how you can align with them to save you time, money, and headaches. So if you understand better how the engineers, if you understand better how they work, how they operate, then you can kind of improve your communication with them so your outcomes can be more aligned to your business needs. So the first, comments about this is engineers, they operate under natural and physical science, mathematics, analysis, engineering design practice, codes, and liability. So we're trying to avoid the risk, especially in structural design. If there is something that can go wrong, let's put more, more concrete or more steel because we want to avoid any liabilities or any problems happening there. We're designing for safety. That's one of the criteria, right? On the other side, we have the shared businesses. And for the shared business owners, what they want is to operate under margins. They need timelines and they need to match client satisfaction. And sometimes the communication is not as it should. So first, I would like to go over who is this workshop for. So if you are in the business of structural steel, that's not going to be applicable for you. I'm going to be focusing more here on the cold formed side of things. We can do another code structural steel with web trusses and universal beams in another workshop. This is more for shared businesses in Australia using cold formed frames such as Cs, Zs, stop heads, etc. So a lot that we're going to be covering here is related to the design of cold formed steel. There are very good books from the ASE. This is one of them. That's the cold form steel structures from Professor Hancock. That, by the way, it's pretty much an early adopter of this cold form steel, and a lot that we do in Australia today is, comes from his work. So let's thank him for the job he's done on all of this. So that's what governs the structural steel, sorry, the cold formed steel design. So now let's go to assumptions, right? So every time an engineer makes a decision, if it's gonna have knee bracing or not, if it's gonna be pin or fixed connections, if it's gonna be site specific or generic, I'm gonna go through in details in each one of these assumptions and showing images so you can understand better. But every time that we change these assumptions, the outcome will be different. So if we have 5 engineers in a room and you give them the same project to design, they might have different assumptions and you might end up with 5 different projects. So how do you actually get the more competitive one, the one that works better for your company? This is what you're going to see here. So these different assumptions, they can lead to frustration because the shared owners, they see this as inconsistency. It's like, oh, another engineer does, this more in a more aggressive way. So they think that's better. And the other one is very conservative. So they think that's not ideal. But both engineers can be totally right. And we're going to understand better that process in this workshop. So by the end of this workshop, I hope you leave here understanding it better. So when you're talking to engineers, you know what to talk to them. So they provide what you need. Okay. So which option is more conservative? Which one is more aggressive? Let's do a very nice experiment here. So let me just move here you to an Excel spreadsheet to show you some of these assumptions or project variables. So imagine you're designing a specific shed, right? It's the same shed, and you send to engineers, and they say, look, I want you to tell me what's the more conservative frames for these sheds. There are lots of assumptions and variables that we can go through. One example of this is, hey, are we going to use knee bracing or not? Are we going to brace the roofs? Do I want to brace the whole roof? Do I want to brace every other bay? Or, hey, I don't want bracing. It's too hard. Do you want to brace the walls on the sides? Do you want to brace the walls on the end? Do you want to use fly bracing? What connections do you use? Is that going to be pinned, fixed, partially fixed? We're going to jump into that later. What's the wind region? It could be wind region A, B, or C. What's the building class? Is it a garage? It can be importance level 2. Is it like a farm shed isolated? It could be importance level 1, depending um, on some regulations. What's the TC? What's the terrain category? Is it going to be 1? So pretty much that's kind of in front of the ocean. Or is it going to be 4, like in the middle of Adelaide, city center? What's the shielding? What's like profiles are we using? Are we using just regular Zs? Are we using super Zs? Are we using top hats as purlins and girds? Are we using C-frames? So do you want to use mullions in the end walls? If it's a drive-through shed, then we don't need mullions. Are we doing concreting or not? The concrete can, help on the resistance there and, be create more stable footings for you. Do you want to make smaller columns and rafters in the end walls? There are some franchises out there who sell sheds that they do the end walls with smaller frames than the mid ones to kind of save a little bit there. But sometimes that savings, it's gonna create more complexity in the erection. So do you want to do this or not? So do you want to, is your shed, does it contain roller doors in all of these sidewalls? If that's the case, for example, when you're doing a storage shed, then you might have a lot of additional strength stress on the fascia, right? So that's something you need to consider as well. What's the bay length? We could be using 3.5, 4.5, 6, 5. And what's the type? Is it an open shed? Is it an enclosed shed? Is it a semi-open shed? So I'm putting here different assumptions of variables, and I'm not going here in very detailed assumptions in terms of the structural engineering calculations. I just don't want to overcomplicate it. I just want to show to you that the same shed, in terms of the size of it, in a location can have different assumptions for that calculation. And if we start multiplying, for example, hey, I have 2 options, use knee bracing or not. I have 3 options for roof bracings. I have, 2 options, 2, 2, 3. So I'm just multiplying all of these here, just so we can see the number of possibilities. This is going to have to be 18. So the number of possibilities for a simple box shed so far would be 29,859,840. If I didn't multiply anything wrong. Yes, that's the amount of different possibilities we could get. But obviously, I'm using here very, general, general assumptions. And depending on your shed business, we can diminish this a lot. So for example, let's say that, hey, I'm not going to use knee bracing on my sheds. I want to brace every other bay. I want my sheds to use bracing on the first and last bays. I don't want to use wall bracing. Let's use fly bracing. My connections are going to be pinned. So let's say bracket connections. It's going to calculate this for in region A, importance level 2. Terrain category, that's going to depend. So I'll leave that for the specific site specific to provide me with the information. No shooting factor, profiles, please do with top hats, mullions and end walls, let's do it. Concrete, well, it depends on the project. Some might have, some might not. So you can see that I'm starting to reduce the amount of variability, but still I have 120 possibilities for the same shed. And I'm not talking about changing sizes, height, width, length. I'm just talking about some specific variables and assumptions that we can, decisions we could make when designing that shed. So can you see the amount of amount of assumptions here. So this is why sometimes an engineer will design something and they would add an assumption that doesn't necessarily match your business needs. So you need to be very specific with them about what you need. Some companies, if you are an existing shared business and you are using a specific software out there, they will have some of those assumptions baked in. The advantage is because it simplifies, so you get the outcome without a lot of back and forth. But the disadvantage is that everyone using that to have pretty much the same outcome, so you don't have much variability. So when you have a more custom shed or custom company that you're doing welded connections, for example, then you need different solutions. And I guess this is where ShedMate helps a lot, because no matter what are your assumptions and variables, we could work with your assumptions for your business. So you have customers using top hats, you have customers using Z, you have customers using fixed connections, you have customers use pin connections, and the engineering design will change from company to company, which matches their specific needs. Okay, so going back to our slides here, I have a very good example to show you. So this is exactly the same shed, but we're using different portals. So this one here uses 5 portals, while the other one uses 4 portals. The one using 4 portals has a total price for that shed of $25,200, while the other one using 5 portals, using 224, has a total price of $23,000. So you can see that we just changed one of those assumptions here. Instead of using a 3.5 maximum portal length, we use a portal of 4.5 maximum, which was in fact 4.3, more or less, meters long. And that's pretty much $2,200 of difference. It's exactly the same shed. So let's look at another option here. This one, he's using a C150-24 and 5 portals as well. And the price is $23,300. So if you compare to the other one, this one is using a C224, the other one is using a C150-24. So if you're just looking at those frames, you might have the wrong representation of the engineering outcome. You might say, oh, this is not good enough. This one would be the best one because it has a C150 instead of a C224. But the other items you need to consider when pricing. So in this example here, we have some knee bracing. Because we are having additional bracing here on these walls, we need to increase the mullion sizing and probably the mullion footing, which is gonna make a difference as well. So can you see that, we have 3 different assumptions here, 3 different shed pricing. So the only way I could find that pricing is because ShedMate allows me to play with the numbers, and I can see how much that change that I'm making is going to impact on my shed. So this is a very good way to find very optimized solutions that match your business needs, not like a general system that gives you an end outcome, a fixed outcome. All right. Now let's cover some principles that we can that can give us some base so we can cover those assumptions in more details. And one of them is about the cold formed steel and buckling. Right? So unlike hot rolled steel, I'm talking here about the universal beams, universal columns, the structural steel or fabricated steel, as different people call it different ways. Cold formed is what we call thin walled. So as you know, the cold form is very thin. So the failure isn't just about stress, but about geometry. I don't want to overcomplicate here, but just follow this with me, and I think it's going to make sense. So buckling is what one of the things we need to assess when you're doing cold formed steel. And what's buckling? It's a deformation of a structural component, such as a column or plate, under a compressive force. So here's a ruler I have, and it's very thin, as you can see. So if I apply a compression force, what's going to happen is this ruler is going to bend. Right? Can you see it's bending? So this is exactly the same thing that happens when we're doing the design of cold formed. It's very thin, so it bends. It doesn't need a lot of stress to bend. And there are different ways that this bending or this buckling can happen. One of them is local buckling. So as you can see here in this image, and local buckling is very tricky because it can actually happen over short periods, short lengths, even 60 centimeters long. So when you're talking about shed design, so to quickly open ShedMate here to go through this process with you. Zoom in a little bit. So for example, local buckling could happen every 60 meters. So no matter the amount of fly bracing I put here, there could still we could still have a local buckling because it's every 60 centimeters. And we don't want to do bracing every 60, or 600 millimeters. That's not, practical whatsoever. So this is something that, we assess when doing the analysis. The other one is distortional buckling, which is the cross-section shape changes through the rotation of flanges and webs. And then we also have the global buckling. That's where the entire member deforms without changing its cross-sectional shape. Once again, I don't want you to be very worried about the complicated terminology here. I just want you to understand that buckling exists. Remember the ruler? Buckling exists, and this is what we assess very consciously when doing the design of these kind of types of buildings. This here is what we call the signature curve. That's pretty much the buckling stress and the buckle half wavelength. So this shows this, which is very popular in the more scientific world of structural design for this guy. Let's move forward because that gave us that base. So, okay, Arthur, you're talking about all of that BS of buckling. What does that mean for me? It means that this is why you need bracing. I've talked to some shed businesses who they don't like bracing at all. I know it can be a pain to erect, but if you don't have bracing, you need thicker materials. Remember, you need a thicker ruler so it doesn't do this, right? So this is the price you're paying. If you need a light design, you need bracing, right? So you need knee bracing, you need roof bracing, you need wall bracing, you need fly bracing, because the fly bracing, knee bracing, all of that is going to act as an item that's going to reduce the total length of that specific ruler. So now I need to put a lot more strength to actually bend it. But if I have the item there, just like a rafter, look, this could bend very easily. But when I add a fly bracing here, then, okay, it becomes harder to do it. So this is pretty much the principle around it, right? So an engineer will specify the bracing to reduce the buckling lengths, as we just discussed here on the ruler. So the length won't be the whole ruler will be pretty much from here to here. So now it's a lot harder to buckle, to bend it. We're gonna do this to control sway and to satisfy code requirements. So in ShedMate, if you're using ShedMate as a designer, there are many ways to do this. So it's very simple. When you come to the system, you go to structure, and then you can add fly bracings, you can add apex bracing, you can add knee bracing, or you can add all of them. And there are lots of rules you could use to pretty much how you want it to be. Like, do you skip the first purling set? What's the maximum spacing you want for them? For the knee bracing, for example, what's the distance from the fascia? What's the angle? Is there any offset? So as you can see here, I'm kind of making some changes, and ShedMate is reflecting those changes in the system there. I could flip it around. So there are lots of different configurations, and it's very easy to do because you're not modeling each of these as you would do in AutoCAD. You're pretty much setting the configurations. That's why ShedMate is a configurator. And then ShedMate is going to apply all of that for you, and you can see the impact of that in real time. Okay, so let me just remove this here, and let's have that shed without any bracing. Let's go back to our discussion. So we understood the importance of bracing, and something else that can vary a lot is related to the connection. Just a moment. Thank you so much. Just got some water here to keep going. So the connections are pretty much the way that we as engineers, we will specify how, for example, our column is gonna be, the interface of the column with the footings will happen. So there are lots of different types of supports. I'll just cover these two because they're the more popular ones. One is what we call the fixed support. So for fixed support, imagine that I have this ruler here, and I am fixing this in a way that if I try to rotate this, it won't go. So when I do this, it creates some stress on my hand, which would be the footing, right? And this force times distance, that's what we call momentum. So that would create some momentum that creates some stress, some internal forces here on my footings. And then we have something that we call pinned support. So the pinned support, just imagine a pin. That's what I'm doing. I'm pinning it. So it still allows me to do this kind of movement. It won't create a lot of stress on the footings related to that momentum. However, I cannot go up and down because it's pinned. So this is the uplift and down lift that's happening here on my footings. So what's the consequence of these different types of footings? If I'm using a fixed support, I might need lighter frames, but my footings might be, a little bit bigger. If I'm using a pinned support, then I might need stronger frames, but my footings might not be that big. And obviously, it depends. I'm just giving here a generic example. And the pinned, because it has this kind of movement, it requires more bracing. So this is why when you're using bracket systems, we might need more bracing, and that's normal because this is not fixed. And the loads are transferred to the column and footings, and in some cases you can have bigger footings and smaller frames. So there are lots of different designs out there in the market. So for example, this here for this RHS frame, as you can see, it's welded and it has a base plate with 4 bolts. So this is a lot stronger than this one here that's kind of pinned. And this column here is pretty much has the possibility of that movement. So when we define different connections, we need to define the assumption will change and the calculations will change as well. So if you're trying to compare a fixed connection with a pinned connection and you want the frames to match, well, you're trying to compare apples with bananas. So you need to understand that these will create different outcomes. Okay, so it's all about your company settings. Once again, this is why a shed is not only a shed. There are lots involved in the shed design, but we do have companies using ShedMate for engineering, use fixed connections, they use welded connections, and we have companies using pin connections. And the engineering for them will be different, right? It can be very close in terms of the pricing and design, but it will be different because the structural analysis will be different for those. So that's another example of assumptions that will vary. Another assumption, this is very, very important, it's site-specific and generic computations. So many reports, they use generic library of computations. They were built before 2021. So if your shed business operates with an Excel spreadsheet that has some calculations, and especially if that was done before 2021, I'm sorry to say that, but you might be not following the code, right? Because the wind load design was updated in 2021. And if you're not using site specific, you can go wrong in your shed design. This is very common still in companies who use a library of computation, and they've done this once with their engineers, they calculate the shed, and now they use that for every shed they're selling. The problem is, look, private certifiers, they're being more and more picky with that. So you might have troubles, and you might be making mistakes that we're going to see here in example of 2 sheds using site-specific against generic computations. So this library of computations, they can serve still the base for many applications and still used by shed businesses. But as I said, there are many pitfalls. If it's generic, it might not follow the coding standards and it's not accurate for every site. So let's understand the workflow for structural steel design. And then we're going to go to this site specific so you can understand better the impact and the importance of it. Okay. So first, how do engineers, they calculate the shed? You send the shed to them. Hey, I have a shed that's 10 by 15, 4 meters high. I need you to calculate the frames for me. So the first thing that engineers do is we go to a program. It could be robot structural analysis. It could be space gas. It could be SkySieve or many of the systems out there. And we start by defining the portals, like the geometry, and we define the supports. So for example, if it's going to be fixed or pinned, remember we discussed this already for the, let's say, the footings here. And then we apply the loads. So the loads that we apply are the self-weight of the material. We call it dead load. It's a dead load. And we have the live loads. So just simplifying here, it's imagine someone walking on the roof, for example. So we need to consider that so the shed won't fail if someone decides to walk on the roof. And then we have our wind loads that they're generally the more representative ones. And depending on the shed, we have these no loads and etc. Once again, Don't panic looking at all of this. I hope you can understand the principle. I don't want to be very technical on this presentation. So we're going to have these load combinations. That's pretty much saying, hey, I have the self weight of the material, I have someone walking on top of it, and I have a wind. So when I summarize all of those different, when I sum actually those three different loads, I have what we call load combinations. So the code will give us some formulas to do that. But this is the first step. Once we have this, we run the structural analysis. Once again, there's a lot of mathematics and physical um, involved here. I don't want to overcomplicate, but we use specifically in ShedMate what we call a finite element analysis system that will give us all of the internal forces, displacements, and support reactions for that specific structure. So, for example, here you can see there is some momentum, there's some different forces applying. And you can see here, this is kind of a graph, right, guys? So the larger ones means there are more forces here, and the smaller ones means, hey, there are not very strong forces here. So we'll calculate based on the stronger ones. And on the other side here, we have displacement. So you can see that in red. So that shed will have some sagging, there's some displacement that will happen, and we can identify based on these calculations how much that's going to be. So when we do this, then we go to the next step in which we can get the loads. And once again, if you are an engineer listening to me, you might say, "Oh, you're skipping a lot of steps." Yes, I don't want to overcomplicate. My goal is to just present this to shared business owners in a way that can be easily understood. So when you get all of those forces and the displacements, then we can assess these in different ways. One, we could check against ULS, which means ultimate limit state. So think of it as a safety check. It makes sure that your shed won't collapse under extreme conditions like strong winds, heavy snow, or maximum loads. So this is all about strength and stability, providing the shed can hold up when it's pushed, proving the shed can hold up when it's pushed to its limit. This is the first check. Another check would be the SLS. This is the serviceability limit state. So this is the usability check. So my shed will still be there. It won't collapse, but I don't want it to, buckle too much. Remember? So even if the shed won't collapse, you don't want it to bend, deflect, or crack too much under normal usage. SLS ensures the shed looks right, works properly, and lasts without issues such as sagging roofs, rattling cladding, and doors jamming. And then, can I have another glass of water, please? And then we have the footing verification. So the footing verification is pretty much the uplift, so we can define, how big your footings are going to be. So this is what we do. We pretty much coming back here. We define our loads. We define the structure, and then we run the structural analysis. We look at the results for every single item. So we look at the columns, the rafters, the mullions, the purlins, the sidewall girts, and we check, is it making sense in terms of the ultimate limit state and serviceability limit state? If it is, great. In this example here, as you can see, my end wall girts didn't pass, right? Say, hey, not okay. You need stronger ones, otherwise this is gonna fail. So what do you do? Guess what? We start all over again. We change those girts and we do the same thing again and again, and then we get another result. So there's a lot of iterations that happen here until we find the right solution. So understanding this, then you might start to understand that's not as simple when you send a design and say, hey, engineer, tell me what are the frames. The engineer will send something for you, and then you come and say, hey, you know what? Can I change the columns to something else? The engineers will be like, if it's stronger, yes, make the change. But if it's not stronger, yeah, you could, but I would need to redo this. I would need to go back to my program. I would need to put those items again, and I need to assess these, and I need to make sure that displacement, everything is correct. So are there ways to do this? Yes, but it's generally a time-consuming process. And because sheds, they are not a engineering project that's very expensive for the charges of the engineers, generally speaking, they become the bottom of the list. They're not the top priorities. The structural engineer might be working with a bridge, with a skyscraper, with an industrial project, and then when it comes to this little shed with all of this back and forth, it's just like, oh, that's a pain. And this is when that conflict starts to happen, because the shed business owners, they might not know necessarily what assumptions to tell the engineer in the first place, and the engineer just wants to get it done, and they send the report, and these guys come back, and all of that back and forth, and it becomes chaos. Okay, so to shared business owners out there, what I would say is, look, as you can see, this is not as simple as just doing this and you have your frames. You could have your Excel spreadsheet. Some engineers do that, and they can change a few numbers, and they can, have a good understanding about what's the outcome for that specific shared design. But if they want to do it everything right, they need to follow a process, and this process is not straightforward. So it requires time, right? So understanding all of these, talking about here the different assumptions, I would like to cover now an example for wind loads. And this is a big warning. And I'll restate what I said before. Many reports, they will use generic library of computations. They were built before 2021. And this will say, hey, if the shed is this, let's say 10 meters wide, 4 meters high, and 15 meters long, in region A, that we will, let's say, accommodate for South Australia and Victoria, then you can use these specific frames for that shed. However, that can be wrong, and that's what I want to show here. So I'm here. I'm doing a comparison with two sheds. They're both region A, exactly the same shed. One is in Mount Gambier, so it's in the middle of the town. The other one is in Port Macdonald here. So the Port Macdonald one is kind of in front of the ocean, as you can see. This one here is enclosed in the town. So when we actually do the site-specific analysis, then shed A in Mount Gambier give us a design wind speed of 37.35 meters per second. This is gonna include the analysis of the terrain category, importance level, shielding, terrain category, as I said, all of that. The other one, the shed B, gave us a design wind speed of 40 meters per second. So the outcome for those sheds is, if I was using that generic library of comps, it worked on the left side, but on the right side, on the shed B, it didn't work. I need better wall girts. It's not passing, and I need better footings and mullion footings. Obviously, I'm not considering here the soil reports. That's just a quick analogy, a quick experiment, so we can compare these two sheds. So I just want to bring that up so you can see that if you're using those Excel spreadsheets that doesn't consider the site-specific wind, you might be doing something wrong depending on where that shed's being placed, and depending on the orientation, depending on many different factors. Here's another example that I've done a very similar study. This now is in New South Wales, and this shed A is in the middle of kind of lots of trees there. It's kind of a farm area, and shed B is in front of the ocean again. Obviously, I guess I'm exaggerating a little bit on this demonstration here, but you could build a shed there, right? And as you can see, this example here doesn't pass for the columns, for the rafters, and the column footings. So if you're using a library of comps and it's exactly the same, you're not using site-specific, that assessment could be wrong, because the wind in this case here is, if I'm not mistaken, 47 meters per second. So this is what needs to be assessed. So the wind loads, they can be a problem if you're not using site-specific. That's why it's very important, especially after 2021 with the updates, to review those calculations you have, or use a system that can give you site-specific engineering reports. Okay? So what does change from project to project? When you're calculating the VDAS, like V velocity or speed for the wind, there are a few different factors that will influence that calculation. One of them is the wind region, if it's A, B, C, or D. The other one is the importance level. If it's a domestic garage or a farm storage that, isolated, it's importance level 1 or 2. If it's a terrain category, if it's an open farmland or suburban streets, the topographic factor, if it's on a hill or flat ground, the shielding factor, if there are trees or buildings nearby, and the site wind speed, that's the final calculated value. So we can have exactly the same shed, but we can have different assumptions, not only in terms of the structure, but also in terms of the location, where it's going to be. And this is going to create different designs. So it's very common for shed business to believe that once a shed is engineered, they can use that as a base to design that in other different locations. But we have just proven to you here, and we have shown a workflow that that's not necessarily the case. You can encounter issues if you're using the same engineering. But obviously, guys, we want to be practical here. And that's why this library of computations, they're created in the first place, right? I'm not saying this to say, hey, if you're using library of comps, you're totally wrong, because the engineer who did that for you, he might have used the worst case situation. In that case, you can use that library of comps. However, it's going to be over conservative, because some projects that you could use lighter frames, you're going to have to use the more conservative solutions, because it's considering that higher winds. So I don't see that as a very practical way. So it might be good for you to use a system, once again, that provides you site-specific engineering. Okay. All right. If you don't have a site plan feature, it's very tough to define a site specific engineering criteria. So I invite you to kind of have a go on ShedMate, and ShedMate gives all of that to you, which is very cool. Another thing I'd like to discuss here is in terms of project delivery. A lot of the frustrations I encountered in the past with engineers and shed businesses can be explained by this good, cheap, fast, right? It's like, hey, pick any two. If you want something that's very cheap and very fast, it won't be good. So that was an example. If you want a generic computation that you can have results in real time and you're not gonna be paying the engineers every time, well, it might not be as good, okay? If you want something that's cheap and it's good, it won't be fast. Okay. But if you want something that's good and fast, it won't be cheap. So you got to pick one of the two and understand that it's very hard to have all of those. We're doing our best here on ShedMate to deliver the three, something that's good, that's fast and cheap, but this triangular here, it still applies. So just to summarize and getting to the end of it, discussion about real world pitfalls and misalignments. I had a very interesting case. We had a customer that before joining ShedMate, they were a franchise supplier. I won't name that specifically, but they were one of those big shed suppliers out there. And he wanted to compare ShedMate's engineering reports with theirs, and he wanted to compare to say, okay, I can transition to ShedMate because it's going to be very competitive. And when he first looked at our reports, he said, hey, your report's too conservative. And you were like, what are you talking about? And he said, no, the frames are too strong, blah, blah, blah. And then we asked him, oh, can we actually get the report you're comparing to? So just so we can see what's going on there. And we saw a few interesting things. One of them is the previous engineer that they used a generic wind speed, not site specific. So this specific shed was in front of the ocean, just like the example I showed you. So the design they're using pretty much wouldn't pass, or at least was being done in an effective way. So that was a reason why our design was a little bit stronger, because it was following the site-specific wind reports. Two, this was for a specific sorry guys, my voice is going away. RHS shed, and the report was giving them a high strength grade of steel that was C450 in the report, but the builder had no idea about it. So he was just using commercial steel available. I don't know if in his case it was C250 or C350, but they're not using the C450. So by not following that, pretty much the liability shifts to the builder, because they're not following the engineering calculations. And that was oversight. They didn't notice that. And when we presented it to them, we said, look, I understand why you're saying that our report's a little bit conservative. It's because, one, you're using the wrong wind speed for that project. Two, you're using the wrong grades of steel. So the result was the shed was under designed and the liability shifted to them. So a myth, and that's something that generally comes after this kind of issues, is, all right, I can still use it. I can still use my library of comps. I can still use these, information that the engineer provided to me. But if anything goes wrong, the insurance will pay for it. That's wrong. And that's another thing that I would like to clarify on this conversation here with you, is that if you deviated from a certified design, the liability can sit with the builder, not the engineer. And also, if you think that the engineer will bend the rules, and if anything goes wrong, they go to insurance, the insurance will pay for it, that's also a pitfall. So I'll read this for you. I'll ask for the permission to read this. Professional indemnity insurance does not cover situations where an engineer knowingly provides a design that is unsafe, non-compliant, or below the standard of reasonable professional care. If a design is unintentionally altered against engineering judgment or outside the building code, the insurer has the right to deny any claim. In such cases, liability falls directly on the parties involved, and the engineer may also face personal, legal, and disciplinary action. Insurance is there to protect against unforeseen errors made while exercising professional risk, skill, and care, not as a safety net for deliberate shortcuts. So, if the engineer is not following the rules, the insurance won't cover for it. And even if the insurance covers initially the process, I have spoken with one of our independent engineers that is on our network for ShedMate, and he worked before on an insurance company, and he said, look, the insurance company will find the money in a way or another. They'll look, they'll assess, they'll get the reports, they will try to understand what went wrong, and they will go to the party that did the wrong part, and they'll ask for their money there. So they're not there, their business, so they're making money, right? So they'll find the challenge. So that generally doesn't work well, guys. So don't rely on insurance because that's not right. Okay. So pretty much here to wrap up everything we're saying, I would also suggest you have a look on the cost against safety trade-off, especially using ShedMate. So there are lots of nice experiments we've done in the past. For example, you might use smaller rafters and columns that shed ends, so less material, but you have more erection complexity. So what's the actual better situation? It depends from business to business, right? Some businesses will prefer not to do that, and ShedMate is a great system because it allows you, with your rules on it, to test these different options and see which one is better for you. Also, the stronger shed members, as we have seen an example today, they can reduce the bracing, they simplify direction, and they produce lower labor costs. So even a stronger shed can be cheaper overall because what you're saving steel, you lose in erection, labor, delays, and reward. Some takeaways. These are some practical advice I would provide in terms of having that discussion between the shed business and the engineers you're using. So the first one is always clarify those assumptions. As we have seen here, don't just send a design to an engineer and say, "Hey, design this for me." If you, as you have more and more experience on the sheds that you're designing, provide more information to the designer. Tell them specifically how you want it and understand the impact of it. As I said, if you're using a knee bracing, you might, benefit from a few things. If you're using, fixed connection, you might have different results. If you're changing the terrain category, if you're using concreting or not, all of that will vary. And this is why I really like the way that we do this in ShedMate, because when you're in ShedMate, the designer, the engineering, and the pricing, they all work together. So let me update this engineering here for us, for example. Done. And what I mean here is like, as I'm adding things, for example, let me add a roller door here or personal access door. Look what happens on my pricing. So this is going to include that. It's going to cut those, girds. And if I start making modifications here, for example, look, I like this design, but I would like my maximum power length for this specific shed to be 1.1. So this one made the difference, and ShedMate's already notifying to me that, hey, that's pretty much over designed, but that's fine. If you want to do that, then you can see the impact of that on your project. And when you request engineering, this is what's going to come to our engineering department. They're going to see the shed as you design with your preference on it. So if it's going to be 1.2, look what happens on my pricing. Or in this case, it doesn't change much. Let me go 1 meter. There you go. So that's 25.5. And if I go back to 1.2, this is 2507. So there is a little bit of difference there. Another example is mullions. For example, you might just to simplify this, if you're rolling in your own materials, you might say, hey, look, for this shed, everything is 224. I don't want to, cut another frame. I'll just use ones that I have here on the workshop. So let's do these ones 224. So if I go here and change that to 224, my price will go from $25,000 to $25,200. So we're talking about $200 difference. So these are ways that you can actually go through the system and explore different design options and how you want the system to work for your business. And then that can pretty much be taken in consideration for your engineering. Another example here would be the maximum bay length. So in this example here, we're using 3.5 maximum, and we have a $25,000 shed. If I change this to 4.5, then you can see that this actually found another engineering that needs some attention. It needs actually up to 24. Yeah, that's good. That's not bad. So if I go back to 3 meters long, let me see if I have any engineering for 3 meters long. Yeah, that actually became more expensive. See, so all of these assumptions you can make, and you can play with the system to actually understand what works better for your business. Okay, coming back to our slides. Demand side specific wind designs, if you can, specifically if you're doing sheds in front of the ocean, uphill, sheds that are more, let's say, in more aggressive areas, if you're doing a shed that's very high. So you need to consider all of that. If you have lots of roller doors or sliding panels, it's good to do a site specific design. So always do that if you can. And understand that code form design is about geometry, not just stress. So we discuss about the importance of having the bracing to remove that total length. So the bracing will, work as a way to reduce the total length of that specific thin walled element, and then we can have, a better outcome. If you don't want to use bracing, you need to use a thicker material. So these will require, stronger frames. So you need to understand that there is no way around this. This is science. Okay, that's natural science in physics. So that's how it is how it is, and we can change that. Don't rely on insurance as an excuse, and use tools like ShedMate to compare those different options and make smarter decisions when you're designing. And I'm not talking only about the structure, but also when you are talking to the client and advising, you can make modifications here that will impact on the final price. For example, hey, if I add a roller door here, how much is going to be? Look, that should be $26,000. And your customer might say, look, I need that roller door, but I only have $25,000. What can you do? All right, let's try to decrease this to 3.8 meters high. All right, maybe 3.7, 3.6, and then we can, there we go, 25.2 meters, $0.2 thousand. Would that work for you? That's too much. And okay, we can add some additional bracing here. We can, change a little bit there. So you can make these modifications, and as you do that, you can see the real-time pricing impact on your shed. No matter if you're making changes in terms of the structure itself, or if you're making changes related to the shed architectural layout, for example, adding sectional doors, glass doors, sliding panels, windows, spinaways, downpipes, skylights, and as you're doing that, you can see that impact in real time, which is very helpful to make the decisions for you. And to finalize, engineers aren't trying to be a pain, right? They're working under different rules than you are. Once again, as we discussed in the beginning, they operate to remove risk. And once you understand how the assumptions drive the outcomes, you can align with them to reduce the surprises and run a safer, more profitable shared business. And my goal here in this workshop wasn't to turn you into an engineer, but give you the clarity to question, align, and take control of your projects. Something I always like to do is do a quick review after I finish about everything we discussed, and I would like your permission to do that. So very good summary here. There is a shared frustration between shared business owners and engineers, but once again, they operate under different assumptions. Engineers, they're focusing on the natural and physical science, the mathematics, analysis, engineering, design practice, codes, and liability, while the shared business, they operate under margins, timelines, and client satisfaction. This was a workshop for code-formed companies. We covered some assumptions that not necessarily different designs from an engineer to another engineer will be better or worse. It depends on the assumptions for each business. And as every company is different, there is no way the engineer will know about all of the thousands and thousands of different possibilities out there if you as a shared business owner don't provide some of those assumptions that you would like to use on your business. We went through an Excel spreadsheet here comparing the different possibilities and assumptions and variables that just a small shed can have, and we got millions of options out there. So using knee bracing or not, using roof bracing or not, using fixed pin connections, what wind region we're using, what shielding factor, what bay lengths we're using, all of those different variables, they will give us totally different outcomes. We compare using ShedMate different sheds. So one using 4 meter base, oh, sorry, 4 bays, the other one using 5 bays. So same shed, just one portal more, and we could see that the one with one portal more gave us a cheaper outcome, which is great. Another one using 5 portals, but with C15024 using knee bracing actually became more expensive than the other solution. So there are lots of things we need to consider when assessing sheds, not only about the size of the portals, there are other factors that will play to get you a good result outcome. We discussed that cold form steel is all about buckling and that thin walled materials. So it's important that we use good bracing, and we understand that even when we're bracing, there's some buckling that can occur, like the local buckling that could happen every 60 centimeters or 600 millimeters. So it's not only a bracing that's going to solve everything. That's why the engineers, they need to assess the projects. And that means for you as a shed business that bracing systems, they're very important. If you don't like them, you need to get thicker materials. So that's why you're going to end up with probably, let's say, 250 24s instead of 250 19. Okay. We discussed different design assumptions for the connections, if they are fixed or if they are pinned, and how that impacts your footings, how that impacts your overall shed sizing. We also discussed site-specific against generic computations and what are the challenges of using generic computations when we have different wind speeds that can impact your shed design. We went through a very basic step-by-step process on how engineers we do structural analysis. So we start with the analytical model of the geometry of that shed with support types and loads. Then we can run, for example, finite element analysis tools such as robot, space gas, you name it, to actually identify those internal forces, displacements. And then for each of those cases, we can assess against the Australian code designs the load combinations, so we can understand if the shed is gonna be safe and it's gonna be usable. So these are the two main checks. And also we do our footing verification to ensure that the footings we design, they make sense. If it doesn't, we go back and we do all over again with the updated frames. Then we did some assessment of two different sheds, one in Mount Gambier, another one in Port Macdonald here in South Australia. They were using the same, pretty much the same sizing, the same frames, everything is the same. But then what changed was the design wind speed. One was 37, the other one was 40. And at the end, pretty much the one in front of the ocean didn't pass on the end wall girths, so we would need to change that. So if you're using a generic computation and just applying the same for everywhere, this is a very good example that it wouldn't work. Okay. Then I presented another example. This one was done in New South Wales, one in the ocean, another one kind of about 300 meters away from the ocean. And then once again, the one in front of the ocean didn't pass. So the same applies. You gotta pick any of the two: cheap, good, and fast. So if it's good and fast, it's not gonna be cheap. If it's good and cheap, it's not gonna be fast. If it's cheap and fast, it's not gonna be good. And we understood in more detail what impacts the formula to calculate that site wind speed, including wind region, importance level, terrain category, topographic factor, etc. Then I discuss about some real world pitfalls. So just be careful about your engineering report. Have a look if it's using site specific wind or generic wind. Have a look if it's what grade of steel it's using. Specifically, if you're doing RHS sheds, you might be using something that's different from the engineering report, which can cause some liabilities there. And make sure that the regulations that were that project was designed, it's updated. It's not before 2021 when the wind code was updated. And also use a system like ShedMate to compare the cost of different design options, which is very flexible, very easy. So you can adapt that to your business and not just receive some fixed report and try to accommodate for that. So depending on how big your company are, I think you can afford having that level of flexibility to say, hey, this is how I like my shares to be done. Let's certify them based on these specific rules and assumptions. So that's also something that can be done. As I mentioned here at ShedMate, to help companies doing fixed connections like welded and pin connections like bracket systems. We help companies doing sheds with only Zs or only top hats or C frames, you name it. So there are lots of different options out there, and we can accommodate for all of them. So the takeaways from this was always clarify assumptions, demand side specific, understand code form. This is all about geometry and buckling. It's very important. So you need to understand that. Don't rely on insurance and use tools like ShedMate to compare that. Engineers aren't trying to be a pain. And I hope that now you have more clarity to question, to align and take control of your projects, talking in a very good language with your engineers so you can understand better what they're doing so you can get a better outcome from their work. I hope this workshop was positive for you, that could bring you some clarity. If anything wasn't clear, please leave a comment below. Let me know, hey, Arthur, could you explain something more about this specific area? And then we can add future workshops on those different topics. And thank you so much for your participation. I hope to talk to you soon about your shed business and how we can help you double your shed sales without hiring more staff, or franchising strings with profitability on the table. Thank you so much. Have a great one.